So what I want to do is use now these laws of logarithms that we've just been looking at to solve indifferent equations, to investigate functions like this. Let's look at this question and see what it's about. We've got a circuit with a resistor in it, and we're measuring the power across this resistor for different values for current. So current of 1.5 amps, the power dissipated is 49 watts. 4.7 amps, the power dissipated is 5.2, and so on. We've got to prove, and this is where using autograph is going to come in, prove that the law relating current and power is of the form power equals Ri to the n. Those of you who've done some electrical work might know the formula that relates the power, the current, and the resistance. Anybody know it off the top of their head? I squared R. Yeah, I squared R. So in fact, we're going to find that this n is 2. Okay, but we want to try and show that it's 2. And this is a very common thing that will go on in engineering. You've got a set of data and you plot it, and you want to know what the relationship is between these two things. You suspect the relationship is of this form, and you can plot a graph to confirm that it is of that form in the first place, and then once you've done that, find the values for R and N, and that's what we're going to do. Once we've found this formula, we've then got a relationship, P equals Ri to the N, which will allow us to calculate the power when the current is 12 amps and the current when the power is 1,000 watts. So in other words, once you've got a formula, you can then use it. So we've got a set of data, and we're going to use that data to try and come up with a formula that we can use. And that's the power of these things. So if we go to autograph, which is downstairs and we'll be using shortly, this software, you can plot the values. So the first thing I would be tempted to do, or I might be tempted to do, is just literally plot the values. If I want to put these values into the autograph, I go to here, fire up autograph, enter data, which is this button here, enter an XY data set. So hit that button and it allows you to put in the values. X, so in the first case I'm going to put current along the x-axis and power on the y-axis. So x is 1.4 and y is 49. So x equals 1.4. Hit return and it goes to the next data point. Power is 49. Hit return, it goes to the next data point, and so on, and put the values in. And then it will plot these values for you on autograph. Now I did one earlier, as they say, in all the best. Yeah. Which is where? Here. So I put the values on, and now it's some sort of, it's not a linear relationship, we can see it isn't, it's curved. Autograph does allow you to put in an equation like y equals ax to the n, because that's what we are suspecting. It's something like ax to the n, and I can change the value of n using this thing called a constant controller, which is here. Just drag this toolbar along here. This button here, the constant controller, allows you to change the values of the constants in the equation. So if I put in the equation y equals ax to the n, y and x is what it plots, they're the variables, and a and n are the constants. So as soon as I put a constant in, it appears in this constant controller. So if I change n, you can see that in fact it bends the curve up or down because I'm changing the power. So you can see that if I were to fiddle around with the values for a and n, I would be able to eventually get that curve to match the points. But what we're going to do is actually come up with a way of calculating what those points are, and then we can plot, we can change the values of a and n to what we've calculated them to be, and we should find that this curve then exactly matches these points. And we've got a function, a formula if you like, that exactly calculates what the power is for a given current. So that's the idea of it, and to do it we use logarithms. So let's look at how that works. We suspect power equals Ri to the power n. That's the formula that we suspect. And we want to find the value of n and r. So n is a power. So what we're going to do with that relationship, find logarithms, yes, to bring that n down and turn it into a multiply. So the first thing we do is take the logarithm of both sides. Log p equals the logarithm of Ri to the n. So, going to our laws of logarithms, look, there are two that are going to be useful here. One is, if I've got two numbers that are multiplied together, it becomes addition. And the other one is the one that we've been using already, which is when I've got a power raised to another power, i.e. the n's up here, it can come down and become a multiply. So I'm using both of those in this. So what we do is, the r times I to the n becomes addition. I can add the logarithms. So the log p turns out to equal the log of r plus the logarithm of I to the n. So the multiplication becomes addition because we've turned them into powers. And now, like we were doing for the initial equations, that n can then come down and become a multiply. So log p equals log r plus n log I. And again, we can go straight from that line to that line because we're using the laws of logarithms, and we can sort of do that in one hit. Multiplication, r times I to the n becomes addition, so that's where this comes from. And if I've turned it to a logarithm, that n can come down and become a multiply. So we just write that down. Now, we need to look at what this is telling us. And so we need to just review what we know, and I'm sure we've done before, but we just need to review the equation of a straight line. And then we'll come back to this.